Describe the function of automatic storage and retrieval systems. An automatic storage and retrieval system, or ASRS, is a type of computer-controlled machine designed to move material to and from defined storage locations. ASRS can automatically locate and deliver inventory to a conveyor system, manual pickup location, or directly to a workstation. This system reduces material handling labor and increases accuracy and productivity. An ASRS can also be connected to production data systems to efficiently coordinate the flow of material to the process. An ASRS can be constructed in many forms. Large systems, such as the unit load system shown, are used in warehousing applications to store large loads on pallets. Small systems, such as a vertical carousel, can be used at the point of use on the production floor, delivering material quickly to the pickup location. Another form of an ASRS uses robots to move parts and material. Automated manufacturing systems often use robots to transfer parts between a storage device and the manufacturing process. Robots are popular for this application because they can easily be reprogrammed and equipped with end-of-arm tooling to handle a variety of part shapes. Most industrial robots have significant data handling and communication capabilities to perform inventory applications. Robot-based inventory systems can be one of two types: centralized or decentralized. A centralized inventory system provides all materials used in the production process from a centralized location. In some cases, such as the example shown here, the centralized inventory system also returns the completed product to the same location. A robot-based inventory system can also be used in a decentralized application, where the parts are stored at stations throughout the process. Robots retrieve parts from storage devices located at the stations and may attach these parts to an assembly or load them in a processing machine before transferring them to a material handling device for transport to the next station. Describe the operation of a robot-based inventory station. A robot-based inventory system includes a robot and support components such as conveyors and storage systems. Conveyors transport material to and from the robot station. Local storage systems can deliver parts to the robot to store after processing or just deliver parts to the robot. Some robots also have a traverse axis to increase the robot's reach so it can service more storage locations. Several types of storage systems can be used to provide parts inventory to a robot and store processed parts. The type of system used at the robot inventory station depends on the size, shape, and variety of the materials being handled. A horizontal storage pallet holds material precisely within the robot envelope for use in the process. A vertical storage rack is a shelving unit designed to hold inventory while taking up little floor space. Another type of storage device is a feeder. Feeders deliver parts, but they do not store them. A common feeder is a gravity parts feeder. This feeder is a power-free device designed to force the proper orientation of parts for pickup by the robot. Gravity feeders are often used when the inventory has a common shape. Vibratory parts feeders use vibration to move parts along channels within the feeder. The parts turn within the channels as they approach the pickup point. Vibratory feeders are used with small, irregularly shaped parts that are difficult to sort by hand. Robots often provide parts to material handling devices for transport to other locations. If the transport device uses a separate controller, the robot controller must send a handshake signal to the other controller to signal that a part is loaded. Similarly, if the robot inventory system is being used to store finished parts, the material handling device controller must signal the robot controller when finished parts are available for pickup and storage. Handshake communication between the robot and the controller can be performed using discrete I/O, serial, or Ethernet communications. In this example, discrete I/O is used to enable a PLC to communicate with a robot controller. Why would an ASRS be connected to a production data system? Which type of storage system is best for small, irregularly shaped parts that are difficult to sort by hand? What type of storage system is a shelving unit designed to hold inventory while taking up little floor space? What does ASRS stand for? What type of inventory system provides all materials used in the production process from one main location? Which type of storage system is designed to hold material for use in the process and is positioned precisely within a robot work envelope? Describe the operation of a servo robot traverse axis. A servo robot traverse axis is an additional axis that moves a robot along a linear path and can stop the robot at pre-programmed points. Robots with servo traverse axes are often used in mechatronics or FMS work cells to perform inventory functions or provide parts feeding to multiple machines. Servo robot traverse axes increase the work envelope of a robot. Without this larger work envelope, the robot would have to be larger or multiple robots would have to be used to cover the same area, which would increase the overall cost of the FMS. Using a single robot with the traverse axis decreases the amount of programming and interfacing needed. A traverse axis is frequently used in robot inventory applications because it allows the robot to access inventory that is arranged in a linear orientation along the traverse axis. This extends the reach of the robot and allows access to a greater amount of inventory. The major parts of a servo robot traverse axis are similar to those of other robot servo axes. The mechanical system consists of a frame structure, bearing system, and ball screw drive. The bearing system provides a low-friction surface to guide the robot as it moves along the traverse axis on steel guide rods. A precision ball screw drive converts the servo motor's rotation to linear motion. The traverse axis control components consist of a servo motor, position encoder, and limit sensors. A traverse axis is usually driven by a servo motor. This motor is larger than other axis motors because the traverse axis supports the robot's entire weight. The encoder feeds back the position of the traverse axis to the robot controller, like the encoders on other robot axes. The traverse axis also has a home position and over-travel limit sensors. The controller that operates the robot's main axes also operates the traverse axis. When the program instructs the controller to move the robot along the traverse axis, the controller sends power to the motor, causing it to turn at a predetermined speed and direction set by the program. The motor turns the ball screw drive, which moves the robot. The controller uses the feedback signal from the encoder to determine the position of the robot. Describe how to program a robot that uses a servo traverse axis. The traverse axis can be programmed as part of the robot's sequence using either point move or distance move commands. To the robot controller, the traverse is another axis, so it is numbered like any other axis. If the robot has 6 axes, the traverse is considered axis number 7. To reach a traverse axis point, jog axis 7 until it is in the desired position and then record it as a teach point. When the traverse axis point is recorded, the controller stores the current positions of the other axes as part of this same point. A point move or P-move command can then be placed in the program to move the robot on the traverse axis to the designated point. A distance move or DD move command moves an individual robot axis a specified distance. The command should include the linear distance to move and the axis number. The distance is a numerical value, and the units can be a default setting or can be configured earlier in the robot program. In this example, the DD move command instructs the controller to move the robot 15 units along axis 7. The traverse axis can be programmed as part of the robot's sequence by either the distance move command programming or by this command. Which servo traverse axis component provides a low-friction surface to support and accurately guide the robot as it moves along the traverse axis? Which is the correct distance move command to move the robot 22 units along axis 7? A traverse axis is usually driven by which component? The robot controller recognizes the traverse axis as what? Program a robot that uses a servo traverse axis. In this procedure, you will program a robot to move on a traverse axis by using both teach points and the distance move command. Click on the equipment to view the step-by-step instructions for performing this procedure using the selected system. Describe the operation of a robot program that uses discrete I/O handshaking. Like other control devices, robots can handshake with other machines. Robots interface to other intelligent controllers to coordinate production operations. To communicate to other devices, robots often use discrete I/O handshaking. A common application of a robot using discrete I/O handshaking is in a multi-station production system like the one shown. Robots frequently perform handshaking with PLCs. The robot program contains commands that wait for a handshaking signal from the PLC. Once a signal is received, the robot can perform its task. Once the robot completes its task, it sends a handshake signal back to the PLC that its task is complete. Robot programs start with a robot initialization. This sets parameters such as the robot's speed and the units of measurement. After the initialization steps, the next commands are those that the robot uses to perform its routine. This routine is set into a loop that begins with a routine marker. The controller can jump to the marker from other parts of the program. When the robot completes its task, it loops back to this marker. Before the robot performs its task, it waits for an input from the PLC using the Wait for Input command. Once the Wait for Input condition is met, the next program line is the first line of the routine body. The routine body consists of the series of commands that causes the robot to perform its task. Typical tasks include loading and unloading parts, welding, or production assembly. After the robot executes the last line of the program's routine body to complete its task, it sends a handshake signal to the PLC by executing a write output command. In some programs, the program uses a second Wait for Input command to wait for a handshaking input from the PLC to confirm that the signal from the robot was received. The final command, a branch command, causes the program to loop back to the routine marker. An example of a robot program that uses discrete I/O handshaking with a PLC is shown in this graphic. The robot provides inventory to two CNC machines. The robot loads the first CNC and moves out of the way. It then sends a signal to the CNC machine that the robot is done with its task. The robot then moves to the second CNC and repeats the process with that machine. Operate a robot program that uses discrete I/O handshaking. In this procedure, you will operate and test a robot program that interfaces with a PLC program. Sensors on Station 3 will signal the robot when a part is available for pickup. The robot will pick up parts from the 87 TMS3 station and drop them off at the 87 TMS1 station. Click on the equipment to view the step-by-step instructions for performing this procedure using the selected system. Describe the operation of a robot program that uses Ethernet communication. In addition to using discrete I/O communications, robots also communicate with other controllers via Ethernet. Ethernet uses the same cable used to download programs, so there is no additional I/O wiring required. To communicate via Ethernet, robots and PLCs use message instructions. One type is sockets messaging. Sockets messaging is used when Rockwell PLCs communicate with non-Rockwell products. The PLC opens a socket connection with the robot at the beginning of the program. When a robot handshakes with a PLC via Ethernet, the robot program includes variables that enable the robot to send data to and receive data from the PLC. The PLC program includes corresponding variables to communicate with the robot. These variables can be single-bit Boolean variables or variables that contain several bytes of data. PLC program. PLC program. Robot program. Variables are memory locations in the program that can be read from or written to by other devices. They are assigned a name or alias and a specific data type. Data types include Boolean, a true or false value; integer, a 16-bit signed integer; and string, up to 252 characters. Variables obtain their values during operation as data is written to the variable's memory location or alias. When handshaking with a PLC through sockets messaging, the robot uses a wait for input command that waits for a message from the PLC to perform its task, just like with discrete handshaking. The PLC sends an output via a standard Ethernet packet to the robot's read variable when it is ready for the robot to perform its task. The data in the packet provides the robot the information needed for its wait for input command. After the robot has performed its task, it sends a write output variable, again via standard Ethernet packet, back to the sockets message to signal that the task is complete. The robot program then loops back to the beginning of its routine and waits for the next message from the PLC. This example shows how the robot program waits for the PLC input and then moves on to perform its task. Once the robot's task is complete, it sends an output to the PLC to let it know the task is done. These are memory locations in a program that can be read from or written to by other devices. Once the robot completes its task, it sends a signal to the PLC that its task is complete, and then the robot program loops back to the beginning of its routine. What else do some robot programs do? When handshaking with a PLC, what does a robot wait for before performing its task? What devices do robots interface with to coordinate production operations? Sockets messaging is used when Rockwell devices connect to non-Rockwell devices.